Hi and welcome back. We're on the second part of the two-part video of chain rules and their derivatives, okay? Now we understood what a composition of function is. Now we're going to find the derivative of a composition of functions. So that means this is prime, this is prime, right? So the chain rule states the following. The derivative of a composition of function is going to be, keep consistent with the colors, f prime evaluated in G, actually this should have been blue, f prime evaluated in G times G prime, which is called the intern derivative. Okay? This is the major and this is the intern derivative. Okay? Like I told you in the past video, what you have to do before anything, before starting doing derivatives here and there, product, quotient, no. Let's calm down, relax. The first thing that you have to do when you have a chain rule problem is figure out which is the major argument and what is the intern derivative, okay? To do that, we're going to use the same exact examples that we used in the past video, okay? First function is going to be sine x squared. Find the derivative of this, okay? As we saw in the past video, we determined that the first thing that I did to the variable x was square it, and then the last thing, the major thing, was the sin of it, okay? So that means that this right here is f, because it's the major, it's the last step, and this right here is g. What's going to be called the intern function, okay, the first step. So what we're going to do next is follow the rule. Exactly what it says right here, we're going to do right here. The derivative of a composition of functions is f prime, okay? Which is f? Sin, right? Right? What's the derivative of sin? Cosine. And I stop right there. Evaluated in G. What is G? X squared, okay? Times G prime. What is G? X squared. What is the derivative of x squared? 2x. And there we go. Just like that. This is f prime evaluated in G times G prime. It's all about figuring out the order in which the operations are happening at x, okay? Remember, the first thing that we're doing to x is square it, and then we do the sine of it, okay? So, the derivative of the composition of functions right here is going to be f prime, sine derivative is cosine, f prime, evaluated in G, cos x squared, times 2x. We can arrange this to have a little bit of better visual appealing. Let's put the 2x in front. 2x cos x squared. And there you go. Now, the first thing that a lot of students ask is, but why don't we do the derivative of 2x? Shouldn't that be an intern derivative as well? The answer is no. What is the original function? Again, go back to the root of the problem. The root of the problem, the original function is sine x squared. So the sine is f and x squared is g. Those are the only two functions happening. Okay? The only two functions happening are those. Okay? So all you have to do is follow the rule. Sine derivative, cosine, evaluated in g, times g prime. That's it. You don't have to do anything else. Okay? There's no more composition of functions. That's it. Period. Okay? Just determine the two that are acting and follow the rule. Let's do the second example, which was, if I correctly recall, logarithmic of 5x, I think. Natural logarithmic of 5x. Okay? Derivative of this. So again, what we're going to do is find the order of what's happening with the x. What's happening with x? First I multiply it by 5, and then I do the natural logarithmic of it. Okay? First, x is multiplied by 5, then I do the natural logarithmic. That means that natural logarithmic is f, and 5, x is g. Okay? G is the intern, f is the major. So, when we apply the derivative of this, it's going to be following the chain rule. Okay? Derivative of a composition of functions is derivative of f. What is the derivative of natural logarithmic? 1 over x evaluated in g. So this evaluation of x in reality is 5x. Okay? Times g prime. And what is g prime? 5x derivative, which is 5, because the derivative of 5x is 5, equals 5 over 5x equals 5 go away, 1 over x. Oh, that's pretty strange. Isn't that the derivative of natural logarithmic without the 5x? Well, yeah, sure. But if you are very good in logarithmics, you can also take a look at it this following way. Remember that when we have a logarithmic of a product, it's like we have the addition of two logarithmics, okay? So we can do this like this. We have logarithmic of 5 plus logarithmic natural of x, right? What is the property that I'm using? Let me write it somewhere around here. I think I have some space over there. Logarithmic of a times b equals logarithmic of a plus logarithmic of b. Okay? So this is exactly the same as this. The derivative of logarithmic 5 is 0 because this is a number. And then the derivative of logarithmic x is 1 over x, which is exactly what we have right here. Again, different paths, same destination. That's the beauty about math. You can figure things out logically from a point of view. Next video, we're going to do the third example that we did in the past video.